Thank you very much. It's a pity that I can not go uh, go to France this time, and yes, and okay, but it's a nice place, and it's very happy to see many friends there. Okay, so my talk is about the complicity theory in arithmetic dynamics. So maybe I briefly say what is arithmetic dynamics. Our setting is like this. So F is map from X to X, where X is a variety. And in algebraic geometry, I think we have two um, kind of maps which are very natural. The one is endomorphism. So we may ask F in endomorphism of X, or more generally, we can ask F to be a rational self-map. So we may allow that F has some indeterminacy locus. And our aim is to understand the algebraic or arithmetic properties for iterates of F. Okay. So So, we will give two family of typical problems in arithmetic dynamics. I think one class is to study the distribution of some dynamical meaningful subsets. For example, we study the distribution of the orbit of a point. So we denote it by OFX to be the orbit of a point x, and the set of, for example, periodic points. So this is pre-F, and the set pre-F, it's the set of pre-periodic points of F. And there are also other meaningful subsets, for example, the ground orbit or something others. And for example, we have some, for this subset, we can ask some very natural question. For example, we may ask, one, this set of periodic points is Zariski dense in X. And we can ask, when there is a point X in X k bar, so you can think it's a closed point such that its orbit is Zariski dense in X. So for the first problem, problem A, I proved that this statement is true if F satisfies some cohomologically, if F is cohomologically hyperbolic. And for the second problem, there is a famous conjecture called the Zariski dense orbit conjecture. If you believe this conjecture, at least in characteristic Z, it gives answer of the second problem. And this conjecture was proposed first by Shou Zhang in the for a special kind of endomorphism, the polarized endomorphism, and generalized by Americ Campana and Medvedev-Scanlon for general rational self maps. Okay. And another type of problem is the problems from defining geometry. And for example, we have the dynamical Model-Long conjecture, dynamical Marley-Mumford conjecture, dynamical Anti-Alt conjecture, and many other conjectures. I think the name, usually the name is dynamical and plus some famous conjecture in arithmetic in defining geometry. Okay, and here I only present one example. The example is the dynamical model-along conjecture, and we just write the DML for it. It was proposed by Gioca and Tucker. Here, X is a quasi-projective variety over C, and F is an endomorphism. X is a point in X, and V is a subvariety. Then the conjecture say that the set of 10 n such that the Fnx is contained in V. This is a finite union of arithmetic progressions. And here the arithmetic progression is the set of the form an plus b, where a, b, and n are all integer, positive, non-negative integer. And this problem is very open. So only some special cases are known. I think one important case is was proved by Bella, Gioca, and Tucker. One F is étale. And another case was proved by me is F is an endomorphism of A2. Okay, so I think so arithmetic dynamics. So at least it is dynamics. So we can think what's the basic idea in dynamics. I think one very important idea in dynamics is that we want to take advantage of the complexity. So
Junyi,
I think maybe this is some very important aspect of dynamics and different from, for example, algebraic geometry. And so, for example, this picture shows this little finger. He said that Charles isn't Pete. Charles is Lade. So I think this is one important philosophy in dynamics. So in fact, for the two examples, two classes of problem I gave before. So for distribution of dynamical meaningful subset, and for example, the dynamical model-along conjecture, in many of the proofs, we use this idea. We need to take advantage of this complexity. And so I think a very natural question is how to measure the complexity in the setting of arithmetic dynamics. Okay. So maybe we just first back to this topological dynamical system. I think in topological dynamical system, one of the most important invariant is the entropy. So the topological entropy. And if you have arithmetic dynamical system, first you can think it as a topological dynamical system. So X is a variety and it has the Zariski topology. So this makes it to be a quasi-compact topological space. And if you assume that F is an endomorphism, so it's not a rational map, it's an endomorphism, then of course F is everywhere well-defined and it is continuous for this Zariski topology. So a very naive way you want to measure the complexity is maybe you just look at the topological entropy for this map. So we may ask, what is the topological entropy for F for this Zariski topology? So for example, if you can get some interesting number, then it means that you can use this topological entropy to measure the complexity. But unfortunately, the answer is no. So was proved by Fabre, Tom, and me. This topological entropy is always zero. So if you use the Zariski topology, and you view this F as a topological dynamical system, then the topological entropy is always zero. Uh, you have in fact you have two methods to prove this result. One is some purely combinatorial proof, very elementary, and another one is more conceptual. Is you can use this variational principle to prove this um, entropy uh, equality. So basically, this answer just means that this topological entropy is not interesting for this Zariski topology. Okay, so 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 if you want to study this, you want to have a good invariant which mirrors the complicity. Um, you think that this Zariski topology is too weak, and so maybe you back to this complex dynamics. So in complex dynamics, there is a very fundamental result of Gromov and Youngding. The result is as follows. So if X is a smooth projective variety over C, or more generally, compact Kähler manifold, and F is a surjective endomorphism, then the topological entropy of F here is not for the Zariski topology, but for the Euclidean topology, uh, equal to this log of the spatial radial of the pullback action of F on the cohomology group. Here you can just use the singular cohomology. And moreover, the right hand side, you can write it as the log of maximum of all lambda IF, where this lambda IF are the dynamical degree. We will introduce this dynamical degree later. Okay, so I think this is interesting because in general the topological entropy is very hard to compute, but in this case we show that this topological entropy is indeed an invariant purely linear algebra. So and you can see in the first hand set, this is the top. In the left hand side, it's the topological entropy for the Euclidean topology. So it rarely relies on this Euclidean topology. But in the right hand side, especially this dynamical degree, its definition is purely algebraic. You can define it just by some intersection theory. So it is well defined even for rational maps and in positive characteristic. Okay. So we first give some remarks of this Gromov-Youngding theorem. The first remark is that this theorem A is for endomorphisms. So people ask, so how about rational maps? And we can see that the Gromov part is that the topological entropy is controlled by this linear algebra set. This part is always true, even for rational self-map, and this was proved by Ding and Sibony. And the another set, the Youngding set, is not true. I think the first example was given by Vincent Gage, and I think the key point is that this topological entropy is not a birational invariant. So Fabre he asked the following question. So because this topological entropy is not birational invariant, so he asked, is there a birational model uh, x prime f prime of our original dynamical system xf such that we can make the equality hold, or maybe not exactly equal, but for every epsilon, we can find some birational model such that the equality holds up to some epsilon. Okay, I think this is the first remark. The second remark is that in theorem A, it is over the field of complex numbers. So it's very natural to replace C by other non-Archimedean fields, such as QP or the field of Laurent series. And Fabre, Tom, and me, we show that the Gromov part is still holds. But in general, the Yangling part is not true. In fact, it was proved by Fabre and Letellier in the dimension 1 case, and by Fabre, Tom, and me in any dimension, that the topological entropy is always zero if this F has a good reduction. So um, even for endomorphism in this non-Archimedean field, the entropy, the Yang part cannot be true. And the third remark is that if X is not scalar, then this Gromov part is not true. And the example is as follows. So if you take gamma is co-compact lattice in SL2C, and X is the quotient SL2C quotient by gamma, then you consider the floor phi t from X to X given by it sends G gamma to this ET E minus T G gamma. And because you see that there is one direction repairing, which is repairing. So if T not equal to 0, you can show that the topological entropy is always positive. But you see the action of this phi t is indeed identity in the cohomology group. So the right hand side of theorem A is just 0. So it means that the Gromov part is not true. Okay, so as we already showed that in the complex dynamical system setting, at least for endomorphism of smooth projective varieties, the topological entropy can be written by some dynamical degree. So I think it's very natural to think this dynamical degree as some analog of entropy in this algebraic algebraic dynamics. So now we give the definition of this dynamical degree. So let X be a variety defined over a field, and let F from X to X be a dominant rational self-map. Okay, maybe we ask X to be a projective variety, and F X to X be a dominant rational self-map. And now we pick L to be an ample line bundle on X, and we think this L as some metric on X. Uh, then we denote by x prime to be the graph of f in this product space x tends x, and pi 1, pi 2 to be the first and the second projection from x prime to x. So for every I from 0 to d is the dimension of x. We define the ith degree ILF. So this ith degree, it depends on the metric L. So it's as follows: it's pi 2 star L. Then we do the intersection I tens, and then intersect pi 1 pullback L d minus I tens, and then you get a number because each term pi 1 pullback L or pi 2 pullback L, it is basically a divisor, and so it's codimension 1, and you intersect d codimension 1 things, then you just get some points, so you get a number, and you denote it by the degree I the ith degree of f with respect to this L. And the ith dynamical degree is defined to be this limit of degree IL Fn, but you take 1 over n. And in fact, it is a non-trivial fact that this limit exists. The existence of this limit is proved by Ding and Sibony in the oversea, and by Tong and Dang in any characteristic. And one can see that this dynamical degree is a very good invariant. First, it is intrinsic, means that it does not depend on the choice of your metric. It does not depend on the choice of L. And it is a birational invariant. So, for example, here we only define this dynamical degree for projective variety. But because it is a birational invariant, so you can define it for any variety, any for example, even for affine variety, you can still define this dynamical degree, because you can define it as any projective compactification, and you define it to be the same number, because it is a birational invariant, so it does not depend on which compactification you use. Okay, and it has a very good behavior, because you see that the lambda I of the iterate of f, so lambda I fn, it is exactly lambda I f the nth power. And there is an important fact is that this dynamical degree lambda I is log concave, which means that lambda I square is large equal to lambda I minus 1 times lambda I plus 1. And this is a consequence of the Hodge index theorem. So I want to give more explain to this dynamical degree. For this, in fact, I want to introduce another invariant. It's very simple from the dynamical degree. I call it the cohomological Lyapunov exponent. So for every I from 1 to d, we just define this mu IF to be the quotient lambda IF over lambda I minus 1F. And for the convenience, we define this mu d plus 1F is just a z. And because this lambda I is log concave, so it shows that this mu I is, in fact, is equivalent to say that this mu I is decreasing. And we think that this mu I is some analog of the Lyapunov exponent in the algebraic setting. So I think the idea is basically like this. So if you pick some random subvariety of dimension I, and then you do the iteration, you can look at volume growth. You can look at the volume growth of this subvariety, and this volume group growth should be the log of this the i's dynamical degree. So it should be log lambda I. But if you think this dynamical system has if you think this dynamical system um, as some kind of hyperbolic dynamical system, so you have some decomposition of the tangent space, and if you iterate some random piece of small piece of some I-dimensional subvariety, and this subvariety is contained in some random direction, then if you iterate it many times, then it will contain the first I direction which has the fastest speed. So it means that if you it means that this volume growth is basically the the sum of the speed of the first I the fastest I directions. So so it shows that the log of this mu I should be the speed of the i's fastest direction, uh, which is the i's Lyapunov exponent. So yes, so basically we think this log mu I should be the analog of the the i's Lyapunov exponent. Um, but we don't want to have too many logs. So we just drop this log and think this mu I to be the cohomological version of this Lyapunov exponent. So this leads to a very important condition. So so we say that this f is cohomologically hyperbolic. Just means that all mu I not equal to 1. So because we say a dynamical system is hyperbolic, means that it's for in any the in any tangent space you have some you can decompose it to some expanding part and some retracting part. So you do not have somewhere this Lyapunov exponent equal to 1. So I think this should be a good analog in this algebraic setting for hyperbolic dynamical system. Okay. So here is the graph. Here I want to explain why we think this dynamical degree is very important in arithmetic dynamics. And we can think this dynamical degree as some algebraic complexity of the dynamical system. And I think it controls this dynamical system in many aspects. So, for example, we have already seen by this Gromov-Yangding formula, this dynamical degree controls the topological entropy. And in the arithmetic set, there is a very important notion of this. We call it the arithmetic degree, which measures the arithmetic complexity. I think we will introduce this. We will give the definition. I think maybe in the third lecture, in my third lecture, and a very important conjecture in this direction is the following Kawaguchi-Silverman conjecture. They say that if our dynamical system is defined over Q bar, and if a point whose orbit is Zariski dense, then the arithmetic degree, so the arithmetic complexity of F for this point is indeed the first dynamical degree, so it's purely algebraic. So this arithmetic degree is indeed controlled by this algebraic complexity. And in some geometric set, I think the dynamical degree also gives some control of some geometry of this dynamical system. For example, for the fibration and for the periodic points. So a very important result is the result of Diller-Favre and Giatulin. They show that in the surface case, if F is birational, in the surface case, if the first dynamical degree equal to 1, then this F preserve fibration. And as I said before, so I showed that if F is cohomologically hyperbolic, then the set of periodic points is Zariski dense in X. So I think we can think this result as some analog of some conjecture of smell. So I think there is a conjecture is that if you have some Alonsoff map, so then the periodic point is dense in the Euclidean topology, and I think this can be seen as some algebraic analog of this conjecture. And also the dynamical degree, you can think this at, for example, for endomorphisms, the dynamical degree is the spectra of F on the numerical group, and some standard conjecture tell you that if you believe the standard conjecture, you show that this numerical conjecture and the cohomology group, they are basically the same. You can control the cohomology group from the information of numerical group if you believe standard conjecture, and so this dynamical degree also control this action of cohomology, and a very famous result of the linear is the proof of Weiss-Riemann hypothesis. You see that if F is the Frobenius over this finite field, then basically Weiss conjecture basically say that this lambda I, the dynamical degree, equal to the spectrum of this F on the H2I for this QL cohomology. Recently, I proved that this is true for any endomorphism. For any endomorphism of smooth projective variety. And this, in fact, proved a conjecture of tone and a conjecture of Tate. Okay, this is for the action of cohomology. And there is also an aspect of, and there is an analytic set. So we think that if F have some kind of hyperbolic condition, so for example, if F is cohomologically hyperbolic, uh, people think that in this case we should have some canonical current or canonical measure, and uh, pe- many people work in this direction and has a lot of interesting result. I think there are Dean, Siboni, Kanta, Johnson, Gage, and many other people for this construction of canonical measure and canonical current. Okay, this is an analytic aspect. So, so I think this explains why the dynamical degree is important. Okay, in this lecture, I think the first proof I will give is the proof of the existence of the dynamical degree. So we want to show the limit exists. And here I follow the argument of Dunn. First, we give some notation. So we say a model of X is the following things. It's a map. It's a birational morphism pi from x pi to x, where x pi is a projective variety, and the map is a regular map, and it is birational. And we define this the ch tilde ix. So it's the inductive limit of the ith Zhou group of all these model, all these birational model. And for every class alpha in some model, alpha in some Zhou I x pi, we identify it with its image in this inductive limit. Okay. And we say this class alpha is defined on this model x pi. And using this, we can get many. We can get some very natural notion. For example, we can define the pullback for every rational map y to x. We can define the pullback by g star from the Zhou tilde ix to Zhou tilde y. So the definition is something like this map G is just rational, but you can always take some model. You can always take some model to make this map to be a regular map, and then you can pull back the class using this regular map. And you can also define this intersection. So from Zhou I tilde x and Zhou j tilde x, and you do the intersection to Zhou tilde I plus jx. And you can define this degree map. So if the d is a dimension of x, then this Zhou, any class in the Zhou dx, you can count the number and get a number in integer number. And I think the proof is the definition is always like this. You go to some sufficiently high model, and you do this pullback and intersection or degree, and then you get what you get this definition. And you also have this notion of positivity. For example, if for the codimension one case, alpha in this Zhou delta Ix, it is indeed a nine bundle on some model. So we say this alpha is naive or big. Just means that in the model alpha is defined. It is naive or big. And for higher codimension, alpha in this Zhou I tilde x, we just write alpha large equal to zero if for every dominant and generically finite map y to x and h1 to hd minus 1 um, h1 to hd minus I in this peak tilde y, which are naive, then the intersection alpha intersect h1 to hd minus I is non-negative. So we use this intersection to define this positivity of alpha. So basically we say that alpha is we say that this alpha is positive if and only if its intersection with some naive class for any the intersection of them with any naive classes are naive, and it preserved by any dominant and generically finite maps. Okay. So I think the key ingredient of the proof of Dang is this Schuss inequality. So it says that if you have two line bundles on some model, so LM, which are naive, and you assume this M is also big, so D is larger than zero, then you can control L by this M. So it's L less equal to D times this intersection number L times MD minus 1 over MD times M. We need to generalize Schuss inequality to any not just in codimension 1. We need to use it in higher code. We need this higher codimensional version of Schuss inequality. We just call it HS. It was proved by Dang and also by and later Jiang and Li. They make the coefficient to be optimal. So the statement is like this. So for I equal to 0 to D, and you pick line bundles L1 to Li and M in peak tilde x, and they are assume they are naive, and MD is strictly larger than 0. Then you can show that the intersection L1 to LD, L1 to Li, this is less equal to some constant only depend on the dimension D and I times this intersection number L1 to Li times MD minus I over MD times MI. Okay, basically it says that you can use this MI to control the intersection from L1 to Li, and just use some intersection number for this L1 to Li to this M, and there is some coefficient, and in the paper of Jiang and Li, they gave this optimal one. But in fact, for our proof, we don't need the optimal one. For us, any coefficient is sufficient. And if you use Dang's proof is given by some induction argument, and the argument of Jiang and Li is using some multi-point or concave body. Here we will give the proof using Dang's argument. Okay, here is Dang's argument for this higher codimensional Schuss inequality. First, you can approximate, you use this continuity, you can approximate all these line bundle we mentioned, this Li, L1 to Li and M by some ample line bundle, very ample line bundle on some model. So we can assume this L1 to Li and M are some very ample line bundle. And we denote by W the intersection of some general sections of this L1 to Li minus 1. And H is a general section of M. Then by Schuss inequality, we show that this Li, the intersection of Li and W is less equal to d minus I plus 1 times this intersection number. This is Li times M d minus I times W over M d minus I plus 1 times W. Intersect M and intersect W. I think the idea is that you do not use this Schuss inequality on X, you use this Schuss inequality on W. Then you get this inequality. And then you use this induction hypothesis. Use this induction hypothesis, you can show that the intersection of M and W equal to the intersection of L1 to Li minus 1 times H. And then this is less equal to this some constant C d minus 1 I minus 1 times this intersection number and times M I minus 1 times H. I think here is something like you use this induction hypothesis on H. Okay, then you combine these two inequality. If you combine these two inequality, you can bound this L1 to Li by some constant times the correct intersection number, then times Mi. So you get the proof of this higher codimensional Schuss inequality. So as a consequence of this HS, you get the following lemma. So if you have two dominant rational self-map F and G from X to X, you can show that the degree, the ith degree of the composition F compose G is less equal to some constant only depend on di divided by LD times the degree of F and the degree of G. And the proof is also, the proof is very simple. You just apply this HS directly. You show this F pullback L, you do the intersection I times. This is less equal to this CDI over LD times F pullback Li times LD minus I times Li. And the intersection number, you see that the intersection number is just the ith degree of F. Okay. And now you compute this degree I, L, F compose G. So it is just this following intersection number. So T pullback, the F pullback of Li times LD minus I. Then you apply the above, you apply this higher codimensional Schuss inequality. You just get this, it is less equal to this constant CDI over LD degree ILF times G pullback Li times LD minus I. But the last term is just the degree of T. And so you finish your proof. Then if you apply this lemma for some m iterate of f and nth iterate of f, then you directly get the following corollary. So the degree of fm plus n is less equal to some constant times the degree of fm and the degree of fn. So you just write an equal to c times degree I, the ith degree of fn, and c is this CDI over LD. Then the corollary just tell you that an plus m is less equal to an times am. So by Factetus lemma, this you get that the limit of this an 1 over n exists, and you see this is just the dynamical degree you define. It's the limit of degree fn 1 over n, and then you finish the proof. So this shows that the dynamical degree is well defined. Okay, so if you just look at the dynamical degree, if you look at the definition of dynamical degree, you see that you do the intersection of the pullback of some ample line bundle L sometimes, and you do some you do some self intersection, and then you intersect with some power of L until you get a number. So basically, you just have two terms, and if you want to, I think it's very natural to have not two terms but many terms. Then you get the notion of mixed degree, and so basically you can define this mixed degree as follows. So you pick L in this pick tilde x to be some big and naive line bundle. I mean line bundle on some model of x. And for the simplicity, you define this Ln to be the pullback of L by some nth power of f. And the mixed degree is the following intersection number is L m1. Then you do some intersection number r1 and until some L ms of some intersectional number rs. And you can always make it to have the following relation. So you can assume this mi is strictly decreasing, and the powers r1 to rs is non-negative, and the sum equal to d. Because you want to get a number, so the sum should be equal to d. So, for example, the degree, the ith degree of fn, you can write it as lni times ld minus I. So it's it is a mixed degree. And I think we want to use this classical dynamical degree to compute this this mixed degree. For this, I think it's very hard to get the exact number. So we basically we only want to keep the exponential part. So we do the following definition. So for two functions, theta 1, theta 2, from z large equal to z s to positive real number. We say that theta 1 is larger than theta 2. If theta 1 is larger than theta 2, if this limit sup max n1 to ns tends to infinity, theta 2 over theta 1, and then you take the root of max n1 to ns, this is less equal to 1. And we say this theta 1 and theta 2 are almost equal if theta 1 large equal to theta 2 and theta 2 large equal to theta 1. I think this definition, you can think this definition is just if you have some function from the non-negative number as power to r positive real number, then you just want to ignore the sub-exponential part. So the definition is that you just ignore the sub-exponential part. And then you can get the following property. So you can compute this mixed degree and show that this mixed degree L M1 R1 to L MS RS it is almost the product of some dynamical degree. It's lambda Li F Mi minus Mi plus 1. Here, this Li is the sum of from R1 to Ri. And the computation is not so difficult. The proof is just by this Schurz inequality plus some induction. Okay, so how can we use this mixed degree? I think the way to use this mixed degree is to get some kind of recursive inequality. So it is as follows. So we recall this mu I equal to lambda I over lambda I minus 1 is the cohomological Lyapunov exponent, and mu d equal to 0. Then we have the following result. We say that for every n large equal to 0, we denote by Ln to be the pullback of L by this Fn. So it is in peak tilde x. Then for every epsilon in 0, 1, and there is some constant m epsilon larger than 0, such that for every m larger than m epsilon, we have the following inequality. So it's L2m plus this L mu I m mu I plus 1 m L larger than epsilon m mu I m Lm, and we call it Ri means the recursive inequality. And here the inequality means that if you do the difference from the left hand side and the left and the right hand side, it is big. You get a big line bundle. And here we can think it's just an inequality of the line bundle, so it's a codimension 1 case. Indeed, you can get some higher codimensional version of this. We can also get some higher codimensional version of this inequality, but the higher codimensional version is more complicated. So I will not present it here in this lecture. We will only present the codimension one case. And if you just look at this Ri, you do not know why it is recursive. So in fact, you can pull back it more by more tens of by some iterate of f. Then you get the following inequality. So it's L 2 plus n m plus mu I m mu I plus 1 m L n m larger than epsilon m mu I m L n plus 1 m. And you see the last inequality, this is recursive. This is recursive means that each term is similar, just by replace n to some n plus 1. So you really get some recursive inequality. And the proof is not so difficult. You just use this Schulze inequality. So you first compute the intersection number L2m plus mu I m mu I plus 1m LD, and you use our computation of this mixed degree. You can see that the left hand side is almost equal to the sum of to the right hand side. So it's a sum of mu I m mu I plus 1 m d minus j times this intersection number. So L 2mj times L d minus j. And the last intersection number, you can, it is almost the dynamical degree. So it's lambda j 2m. And you can see here is the sum of d plus 1 terms, and it is almost equal to its maximum term. And you can see the maximum, you can achieve the maximum at 1j equal to I. You can see that you can achieve the maximum at the term j equal to I. So it is almost this number. So mu I m mu I plus 1 m d minus 1 lambda I to m. And we call this equality star. And now we compute another intersection number. This L2m plus mu I m mu I plus 1 m L d minus 1 L m. And we do this computation, and it is almost the sum of this mu I m mu I plus 1 m d minus 1 minus j, and then you have some intersection number of 3 terms, L2mj, Lm, and Ld minus 1. And then you use the computation of a mixed degree. It equal to the sum of mu I m mu I plus 1 m d minus 1 minus j mu lambda j m lambda j plus 1 m. And you can see it takes maximum value 1j equal to I minus 1 and I, and you just use one of it. So it is almost equal to mu I m mu I plus 1 m d minus j lambda I minus 1 m lambda I m, and so equal to the last term. So you combine this star and 2 star, you get this quotient. So the quotient of the 2 intersection number we computed is just mu I minus m. Now you can apply Schulze inequality. By Schulze inequality, you show that there is, for every epsilon in 0 and 1. Okay, maybe I I need to explain. So usually we use epsilon to be some number very close to zero. But indeed, in all my talk, epsilon in 0 and 1, you think it is as some number which is very close to 1, but smaller than 1. Okay. Then, so for every epsilon in 0 and 1, and m sufficiently large, we have this epsilon m, Lm, less than mu I minus m times L2m plus mu I m mu I plus 1 m L. And then we get the inequality we have. Okay, so 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 here I want to give some applications. So here I want to give some applications of this recursive inequality. The first application is that we want to study the behavior of dynamical degree in a family. I think one motivation is the following conjecture of Cole and Silverman. They proposed this conjecture in 2018. They say that if F is a dominant rational self-map on PD, having integer coefficient, then they conjecture that the first dynamical degree of F in the generic fiber is equal to the limit of the first dynamical degree of Fp. Here, Fp is the specialization of F at some prime p. In fact, before their conjecture, in fact, it's in my first paper in 2015. I proved this result on surface. So when d equal to 2, this conjecture is true. And I also give an example to show that you exactly need this limit. So the example is as follows. If you look at the following map, it's indeed a birational map, x, y, z to x, y minus 2z square, and yz plus 3z square. Then you can show that the first dynamical degree equal to 2. But if you do the specialization, the dynamical degree is always strictly less than 2. It's always strictly less than 2. So you really need this limit. You cannot say that the dynamical degree equal to lambda 1 Fp for p sufficiently large. This is not true. You need to take the limit. Okay, and so if you want to study this conjecture, you can here it is a conjecture defined over Z, but you can think it as a family of dynamical system defined over spec Z. So here we want to give the definition of a family of this dynamical system on some any integral Nodarian scheme. So here we just ask S to be an integral Nodarian scheme. I think some interesting example is the case S is spec Z, or you can think it's a curve over C. Okay, and D is at least, the dimension D is at least 2. And we say a family of d-dimensional dominant rational self-map, and on X is the following data. Is first uh, a flat morphism pi from X to S, and F is rational self-map from X to X itself over S, such that the following holds. First, first you ask each fiber is xp is geometrically reduced and irreducible, and so I think the first condition just means that each fiber is a variety, and the second condition is that uh, the fiber xp is not contained in the indeterminacy locus of f. So it means that you have this global rational self-map. You can restrict it to any fiber, and you get a rational self-map on this fiber. And the third condition is that the restriction is dominant. Is dominant. And so later we will just call such data a family. So because a family of d-dimensional dominant rational self-map is too long, so we just call it a family. So what I prove is that the following result. So if S is a Nodarian scheme, and this data pi x to s is flat, is flat, and f x to x over s is a family, as in the last slide. Is a family of d-dimensional dominant rational self-map. Then for every index I from 0 to d, the function for every point p in parameter space p in S, this function is from, for every point p, you take the ith dynamical degree of the specialization of f at p, so lambda I fp. Then you get a real value function. Then the result is that this function is lower semi-continuous in the Zariski topology. So it means that for every real number lambda, the set of point p in the parameter space, the scheme theoretic point p lambda I fp less equal to lambda, this is the Zariski closed subset. And the surface case was proved in 2015. And you can see that a direct consequence of our theorem B, it is the following corollary. Is that if you have a dominant rational self-map f from PD to PD of integer coefficient, then the lambda I on the generic fiber equal to the limit of the specialization of f at all primes. Okay, and from theorem B to this corollary, I think the key point is that in fact the lower semi-continuity of the Zariski topology is quite strong, because the Zariski topology is very weak. So this lower semi-continuity of Zariski topology, it in fact implies the continuity at the generic point. So here this corollary is just says the continuity of this dynamical degree at the generic point. And if you ask this I equal to 1, then this implies Cauchy-Siverman's conjecture. Okay. So now we want to give the proof of this lower semi-continuity. So the proof of this theorem B. Uh, for the higher codimensional case, it's more complicated. The higher codimensional case, you need to use some higher codimensional regressive inequality, and so here we only consider the simplest case, so the codimension one case. Uh, Moreover, we ask our variety just the projective space. So this is the most simple case. So here S is just a spec Z, and X is the projective space over S. And we consider the codimension one case, so I equal to 1. And we can pick an ample line bundle, so L is O1. And we denote by eta the generic point of S. So it's very clear in this case, for every point in P and n large equal to Z, the first degree of Fn at P is less equal to the degree of Fn at the generic point. Because our X is the projective space, and in this case, if you want to compute the first degree, it's very simple. You just write down this F in homogeneous polynomials. So it's possible that it's possible that if you view it over Q, it do not have a Gaumont factor, but at some prime P, it's possible that you can have some Gaumont factor, then you cancel this Gaumont factor, then this degree draw down. So you have this inequality. So the degree of Fp is less equal to the degree at the generic fiber. Okay. Moreover, we can show that for every n, you can pick some Zariski open subset such that we get equality in this Zariski open subset because having some Gaumont factor, this is some close condition. So you can just remove some Zariski closed subset, and in this case, it's just remove some point. Then you can ask. You do not have more Gaumont factor, so you can use in this. If you remove this point, then you still get equality. So then you then if you take limit, it's very easy to see that the first dynamical degree of f eta is large equal to the first dynamical degree of fp for every prime p. So if you want to prove our theorem B, we only need to prove the lower bound. So we only need to show that the limit inf of the dynamical degree of fp, first dynamical degree of fp equal to the first dynamical degree at the generic point. And so if you combine these two things, then you get what we need. Okay. So the idea is the following. You first pick a minimum. There is a minimum I such that mu I eta is strictly less than mu 1 eta. We just do this computation in the generic at the generic fiber. So you have first I such that the Near-Proof exponent jump down, and then you apply the regressive inequality for this index. So it means that there is some epsilon in Z1 for every epsilon in Z1, there is some m epsilon such that for every m large or equal to m epsilon, you have the following inequality. So L2m eta plus mu1 eta m mu I eta m L eta larger than epsilon m mu1 eta m L m eta. And for the first term, you see that this mu I is strictly less than this mu1. So you can write it as mu1 eta 2m times some delta m, where delta is strictly less than 1. So we fix this m, then we can find a Zariski non-empty Zariski open subset um such that for every point p in this the inequality still hold at this prime p. So here you look at this inequality, L2mp plus L1 eta 2m times delta m LP larger than epsilon m mu 1 eta m L MP. This equality is similar, is exactly the same as the inequality in the last line, but we just change this eta to p because bigness is an open condition, and then we can pull back it by some iterator of f. So you get this recursive inequality, and we just write it as 2 star. So L2 plus nmp plus mu1 eta 2m times delta m L nmp larger than epsilon m mu1 eta m L1 plus n m. Okay, and I think then here we need to use some very simple things. We need to use the following observation, and we call it the easy lemma. Is as follows. So you have alpha, beta, gamma, three non-negative number satisfy gamma large equal to the sum of alpha and beta. And an is a sequence of real numbers with the following two conditions. The first condition is that a1 strictly larger than beta a0. The second condition is an plus 2 plus alpha beta an large equal to gamma an plus 1. Then we get the following, the lower bound, limit inf an 1 over n large equal to alpha. And we see that here we have basically three conditions. The first condition is this gamma large equal to alpha plus beta. And if you study this, if you just want, I think this is something related to this degree 2 equation. And if you want to solve some degree 2 one variable equation, there is some condition is the determinant large equal to 0 and means some non-degeneracy condition. So I think that this first condition, this gamma large equal to alpha plus beta, we think it as some non-degenerate condition. And the second condition is just for A1 and A0, so it's some initial condition. And the third condition is some recursive inequality. So you can think this easy lemma is that if you have some recursive inequality, which with some non-degenerate condition and an initial condition, then you have these three conditions, then you can get a lower bound of the limit inf. And Okay. I will not prove this lemma because as you see, it's an easy lemma. It's very, very easy. Uh, okay, and if you apply this easy lemma, I think it's you can finish the proof very fast. But I think it's not faster than 3 minutes. So, but I only have 3 minutes to for this talk. So maybe I stop here.
Okay, thank you. So, do you have any question?
Do you use log concavity of the dynamical degrees and the recursive inequalities?
Let me see. I think I need this. So basically, I need this. I need to use that the cohomological Lyapunov exponent is decreasing. So this is equivalent to the log concavity of the dynamical degree.
Okay.
So yes, I used this log concavity of the dynamical degree. Yes.
Other questions?
Do you have an estimate of the speed of convergence of lambda 1 of fp towards the generic dynamical degree?
Let me see. No. So I think the proof is quite is quite theoretical. It's something like we show something is an open condition, so you say that there exists some Zariski non-empty Zariski open subset such that it satisfies this condition. But basically you do not know how large what it is this open subset. You just say that there is some Zariski open non-empty Zariski open subset. So I do not have some estimate of the speed.
Okay. Thank you again.
Okay. Thank you very much.